With section of 3. We have 4 papers, and the first one has the title Towards a Semantic Model for Weiser System, a Graph Matching Algorithm. And will be presented by Abdelhafid Dahami.
Yeah, this is it. Thank you very much.
Please be nice in asking questions because he is streaming and recording, so
yeah,
you will be recorded with the...
For my life, and for me also.
to prevent any difficult questions. Right. we learn. It's the first time somebody said, I want to avoid difficult questions. I don't see.
Right, it's already...
It's on the... You said it's on the...
It's on the screen. Ah, okay, this is how it works.
That one?
Yeah, that one.
Good, you see?
Okay.
Now, you can push the button. It's okay, it's on already?
Yeah, it's on.
Uh-huh,
yeah.
Good.
I am Valencia Conference from Listic Laboratory, and this presentation is entitled Toward the Semantic Model for Weiser System, Graph Matching Algorithm. And more specifically, we will have two formalisms, and we will try to link each other to give one of them the meaning for humans. So, supervised by professors and doctors Sébastien Monnet, Flavien Vernier, and Ilham Alloui attached to Mont University, Listic Laboratory, and Polytech NC Chambéry. The first thing I will present myself. So I'm holding a master's degree in application architecture and development engineering. And now I am in the end of my second year in PhD in data science field. And also I worked with international companies in Morocco, USA, and France as a software engineer and an engineer of innovation. So, to put you on the context, I will begin with a little story about what we were doing in Listic Laboratory. The first thing, the context is the Weiser object. And years ago, my supervisors tried to invent something that could know itself by itself without any human. It's like an object that learns about itself. When we have, for example, a connected object, whether a roller shutter, a TV, a microwave, or whatever, he can learn its capacity, its capability without humans. Also, this Weiser object could be a software, an application, for example, linked to domain of bank or whatever. The current object now have some abilities. The first one is he can get the knowledge about its capabilities. It's like how it's working, its functionalities. And the second one, he can get knowledge about its use. It's like if you are using a TV or you are using a roller shutter, like opening and closing the roller shutter during your day, the roller shutter will know this behavior and will log the behavior you are doing. And he can analyze the knowledge to generate new one based on some rules. Also, he can react according to its knowledge. And to do all of this, he is based on a loop called MAPCA to assure adaptability. It's like he is adapting to your behavior. So, before going further in the presentation, I need to mention that to do all of these abilities, he is based on two states. The first one is so-called the awake state, and the second one is called the dream state. So the awake state, the object can answer any request from humans or from another application. It's like an application that calls another application. This is a request. And in the dream state, this is the most important part in the Weiser object. The dream state, he can do the introspection. It's like he's seeing himself or itself without another third party. It's like a human in this case. And he can activate the learning. He learns about the knowledge gotten during his functioning, and also analyze and do the management of the knowledge. So after working on this process during the training process, he will generate a graph. This graph is called STG, and STG it stands for State Transition Graph. This graph, as we see here, he contains the behavior or the behavior of the object itself. It's like when we have a roller shutter, we will have an STG, a state transition graph, that contains the behavior of this roller shutter. We can say that a roller shutter can open in at level 50, 80, 90, etc. This is a behavior of the roller shutter. And as you are seeing here, this graph is meaningless to human. I can't know what does it mean 0, either 1 or 2. I don't know, except that it's a little bit blurred, except the useless method here, open, close. But I can't know what does it mean 0, and what does it mean 1, and what does it mean 2. So the challenge here is to search where we can find the meaning of those information here without entering the end user in contact with wise objects. So the question here is how to make this wise object able to communicate with humans. It's like how you will communicate with humans using a clear language. Now with this graph, I can say that the wise object will say, I am on the state 0, I am on the state 1, I am on the state 2. But I can't understand what does it mean state 0 is the roller shutter is open or is closed. We can't understand as a human. We can't understand the numerical. As a human, we have a numerical. We have a problem with numerical values, but we can understand the semantics, the meaning. When I say, for example, when the roller shutter say, I am open, I can understand that he's open or closed. So, pushing the wise object to communicate with humans, how and what are the limits of such objects. So, after some literature, we found that using the formalism called IOSS for humans to machine communication will add more value to our STG. So, here, as you see in the title, it's human to machine communication. I will give some information to machine by humans. So, in the previous slide, we were talking from the machine, the machine to human communication, but now we are talking from human to machine communication. So, firstly, why we are using IOSS? IOSS, it stands for Input, Output, State Transition System. It's just a syntax that we can use to describe the behavior of something, and that thing is whether a connected object, physical connected object, or an application. It's like a software. So, why we use this IOSS? It's because in the literature, they used it often in describing the behavior of any systems, and it's commonly used. So, the syntax is here. We won't enter in the detail, but the most important for this presentation, for this first version of this article, we have two localities. What does it mean, locality? Locality is this one, this circle, and this circle. This is closed and this is open. So, this is the conception or the behavior of a roller shutter using an automaton IOSS. It's the syntax. This is how we describe a roller shutter or another object using another version of the IOSS. And here, closed and open contain a lot of states. So closed, one state. Why? Because we have height is a variable here equal to 0, and open we have height is between 0 excluded and 100. So in open we have an infinite states. So the states depend on the height, on the value of the height. The height equal 1, equal 2, equal 3, equal 4, and we end in 100. This is a lot of states. Here we have height equal to 0. This is one state. So we have here two localities closed we have one state, and here we have a lot of states. This formalism will be given by a developer or an expert. So I will draw in the problematic schema to put you in the big picture before going toward the solution used. So the first thing what we have a knowledge here. We have the knowledge already in the Weiser object represented as an STG. Here the STG is not understandable by human. The question raising before is where we can find the meaning of those information that lead us to a semantic problem. Here, as you are seeing here, semantic problem. The semantic is adding meaning to some information that are meaningless to a human. So semantic is giving sense to something. And the answer were in the iOS test, that's the meaning of the system. All of this process is to give the ability to the object to care the semantic, and that implies communicate with humans. So, the solution we use here. We have the first graph here, the second graph here, because there are a graph, but this is STG and this is iOS test. As you are seeing here, we have level equal 0, level equal 50, and level equal 100. And here we have the iOS test with another variable here, height, and here we have same variables. But I have a more specific thing about level here. When I'm talking about level, I mean attribute. Why we are seeing attribute and not variables? Because this STG is generated with a mechanism called introspection using the object, and the object, as we know, if you are all of you from oriented object programming, an object is a simple class, and the class it contains attributes, not variable, by using the convention. So what we firstly to link both graph, we proposed to base on graph morphism to create the algorithm of linking the two graphs and linking this stage with one of the two localities. But we have some constraints. The first constraint is we need a correct iOS test. For simplifying the algorithm in the first version, we are considering that an iOS test is correct only if we have the uniqueness of the localities. It's like there is no duplicated localities with the same sense. I can't have here another locality that contains open. Maybe I can have another locality that contains, for example, the angle of opening the roller shutter, but another open here or another closed here, this is incorrect for our algorithm. And it's represented in this formula here. It's like the intersection of the domain of this variable here and here need to be empty. And as we are seeing here, closed and open are unique. The second one, we need to find the first type of matching. We need to match the level or the attribute here with its corresponding attribute here. That means that we need to search the domain here that need to be included in the domain of this height. As we have seen here, it's blurred a little bit. So the height is between 0 and 100 in this iOS test. And the attribute here, the domain of this attribute here is between 0 and 100. That means that level is represent the same thing as height, and it's represented in this formula. And I need to mention here that we are using just one variable. In an object we may have as much as variable 2, 3, 4, 100, but for the simplicity of the first version, I am using here just one variable to prove our algorithm firstly, and I will show you after the many variables. So, and the last thing here is the state matching. The state matching here, we have this match this, this match this, this match this, based on the value of the variable in each state. So we have here level, okay, equal as 0. So I need to search where is height here that's equal as 0 or contain a domain that contains 0. So closed height equal as 0. So this state match this state, this locality. And here too, level equal 100 and level equal 50. So we know that 50 and 100 is included on height is between 0 excluded and 100. So to make a resume, we know now that the state 0 is the roller shutter closed and the stage 1 and 2 is open. Here is open with the 50% or 50 because we don't have here the meaning of 50 and we have here 100. So all of this to give the semantic to understand this SCG. If we can understand as a human this SCG now, we can give the ability to the wise object to communicate with us and to say open, close. If the wise object, for example, is this case a roller shutter, he's in this state, he will say open. Or if he is here and here, say close. It may appear that these formulas are simple because we are using just one variable. Imagine here, if we have two variables here, and two attributes, and here two variables. The problem will be more complex than imagine. So if we apply the current algorithm on this both graph, we will have these two graphs as a result, two matching. So why we have two matching? We said before that the algorithm will firstly need to be sure that the iOS test is correct. Okay, this is correct. The second thing is searching level orientation. It's matching here height and angle. And the last thing is to matching the state with the locality according to the inclusion of the domain of the attributes in the domain of the variables. Why we have two matching here? Because the algorithm found level is equivalent to height. Because level, the domain of level between 0 and 100 is in 0, 100. And orientation that take 0 and 90 is in the angle, because the angle here in the iOS test is between 0 and 90. And this is okay, this is correct for the machine. From where we got this one? This one is also gotten based on the attribute variables matching. Orientation is also match height. Here, as we see, orientation is between 0 and 90, and 0 and 90 is included in the height that is between 0 and 100. And this is, I can say this is correct, both correct for machine, but for human, what's the most convenient for us? What is the most logical for us? Is this one or this one? This is what we are working, this is our working now, to give the machine or to push the machine or the wise object toward human decisiveness, how he will decide that this one is more convenient for human, but this one is far away to be logical to human, because orientation does not match height using the language that you will use daily in our lives. Thank you very much, and if you have any questions, don't hesitate. Thank you.
Is there any question?
Could you go back to the last slide?
Okay.
So there's two possibilities for matching. I mean, clearly the left one is better because you can match two variables, and the right side only one. Or should choose the left side.
Yeah. So here he's finding that level is equivalent to height and orientation is equivalent to angle, and here he found just orientation is equivalent to height. So it's more deep than that. In details, we are searching the combination. We are trying to maximize the combination of matching. So here, the algorithm says that there is a matching that he can make between level, height, orientation, and angle, and he give us one matching, but he found that another matching based on one variable's matching. You see what I mean? So here I have just orientation and height, but also it's a matching. You see, I don't know if I answered your questions.
So, he doesn't aim to match several variables simultaneously.
Like to use several variables. How you will decide? This is the question. Actually, how we will decide, how the machine will decide that this is more convenient to you, to the end user, and this one is not, because we can have, if we can eliminate, for example, we can add another variable, we will have another matchings. It's more than 2. You see, this is the maximized actually matching. We have just 2 matching, but imagine that we have here 6 attributes and 6 variables here, or in case that we have 6 attributes here and just 5 variables here. It's not necessary to have the equality between the variables and attributes. So this is the most complex thing in the matching of this kind of graph. Okay.
Any other question? Yes.
I disclaimer, I'm a formalist guy, so I pretend I understand the science, not the logic.
Okay.
So I was thinking a little bit of, you have a solution here, and what is the most critical problem you can apply it? And I do suggest, I'll read a little bit more on it and I'll come back later on a few weeks. I do feel that a part of this approach will be very useful for so-called explainability, AI explainability. Because you deal with, let's say, smart objects, kind of, but you try to have a more approach from human life. So, and this is the point. Actually, sorry for taking a little bit more, but the point is that as it is now, it appears that the solutions so far on explainability, in the sense of building the confidence of a user on the solution of AI, it's more complex than the solution itself. So you need a very smart user to understand why is that one. Because the explainability itself is equally complex than the original point. So this kind of mapping might a little bit downgrade the level. So anyways, that's just my point, that this will be one aspect you should start, my feeling, you should start. I promise I will read, because I'm working on explainability, and the only way to learn more is to engage that you will do something. Right? Thank you.
Thank you very much.
And well, I have just a comment. I have a doubt. In that case, in that example, you have 4 different variables, and if you increment the number of variables, you will be able to have more different states, more possibilities, more combinations.
It depends on the variables. Maybe we can, for example, here. So here we have 2 attributes and 2 variables. So imagine that we have here 4 attributes and 4 variables, and each attribute match 1 variable, we will have just 1 matching. But if you have just one of them match 2 here, we will have another type of matching, and we need to apply another thing here, as we are thinking about ontology, to contextualize the matching and to push the machine to near human decisiveness. It's the ontology that we will integrate in this result here.
And it is possible to have different combinations, different possibilities. And for example, the first one was the most convenient for the human communication, but not the best one for the performance of the system.
Yeah.
Okay.
For the performance, we will have a little bit of a problem. This is called I think the knapsack problem. It's like you will, I don't know if it's called the knapsack problem or not, but it's the combinatorial explosion. Actually, you see that much more attributes and variables, much more calculation, if you know what I mean.
Yeah.
And yeah, we are also thinking about this problem, and we found a little solution that it will be explained in our next review. We found this one using the anthology and to contextualize these attributes and this variable here. And we won't be able to go toward all the variables and attributes. We will eliminate a lot of things in the first of the process. That's what we will use.
Thank you.
Thank you very much for your time.
If there is no comment, okay.
Thank you very much.